It is Thursday, December 3rd, 2020. We're continuing with section 5.3 on conditional probability and independence. And today specifically we're going to be talking about the general multiplication rule and tree diagrams. Okay. So first thing we have here is the probability, or general. Oh, crazy. Oh my goodness. All right, we have the general multiplication rule. All right, this is the probability that events A and B both occur can be found using the general multiplication rule. Probability of A and B is equal to the probability of A and B. It's different notation. This is our new notation here. And that's equal to the probability of A times the probability of B given A. Okay. So this is where probability of B given A is the conditional probability that event B occurs given that event A has already happened. Right. Give me a second, guys. My little pen thing is not cooperating. That's better. All right. So, as a reminder from our previous lesson, our conditional probability rule is the one that says probability of B given A is equal to the probability of B or A divided by the probability of A. Okay, this was the rule that was introduced last class. Okay. And this rule here is just this rule where we've gotten rid of the fraction, essentially. We multiply each side by the probability of A, and we get probability of A times probability of B given A is equal to probability of B and A. The probability of B and A is equivalent to the probability of A and B. So the fact that this one says B and A and this one says A and B doesn't change anything. Okay, so this is the new rule that we're going to be using today. So you might need a moment to write any of this down. Please raise your hand. Right. So then, let's look at an example. The Pew Internet and American Life Project find that 93%, we'll need that, of teenagers ages 12 to 17 use the internet. And 55% of online teens have posted a profile on social networking. All right. So before we even get to the question here, we have a couple of things that we can say are true, or some probabilities we can identify. Right? We have the probability that a teen uses the internet. Right? We'll just call this A. Call this event posted profile B. So the probability of A is 0.93. The next probability we have is 55% of online teens have posted a profile on a social media network. Right? But this is of the teenagers using the internet. Right? 55% of the people using the internet. So that next probability is the probability of B given A. Right? Anyone not understand how I identified these two probabilities based on the context. Okay. So again, now we want to answer the question. Find the probability that a randomly selected teen uses the internet and has posted a profile. So again, we have uses the internet, posted a profile, and we've labeled this as event A, this is event B. So I'm asked to find probability of A and B. Well, based on our new rule, we know that that has to equal the probability of A times probability of B given A. Okay. So we get 0.93 times 0.55. And if I'm remembering correctly from the last class, that should be 0.5115, I believe. Oh, yeah. 0.5115 or 51.15%, or we might be able to go with approximately 51%. What can I clarify here for you? Do you have any questions? Right. So you need a moment to write anything down. Okay. All right, next thing we're going to talk about is a tree diagram. Right, tree diagrams help us apply the general multiplication rule while creating a sample space that models the chance process that involves a sequence of events. Right? So in general, this is what these will somewhat look like. We'll have some starting point. Okay? And then there'll be options branching off of that. Right? We might have two options. Right? Say option 1, option 2, and maybe option 1 has a probability of, I think, 0.7, and option 2 has the remaining probability, because there's only two choices, so has to make up the difference to get to 1, 0.3, and then from that, we then have more options. So it could be another two branches for each, and we get the options of maybe like a yes or a no. Right? And maybe if we're given, they chose option 1, the probability of yes is 0.65, leaving 0.35 for no, and maybe this is 0.2, leaving 0.8 for no. This is a general idea of what a tree diagram will look like. Right? We can use known information and given probabilities to fill in the rest that could occur. Right? Is there any questions about a tree diagram? Does anyone need a moment to write or draw any of the stuff from this slide? Okay. So let's do an example. All right. So we've got Mr. Mosley hits the snooze bar on his alarm clock on 60%. There we go. School days, if he doesn't hit the snooze bar, there is a 0.9 probability that he makes it to class on time. However, if he hits the snooze bar, there is only a 0.7 probability that he makes it to class on time. On a randomly chosen day, what is the probability that Mr. Mosley is late for class? All right. We've got some given probabilities. We've got two events, essentially, that have been provided, right, in this context. First event that we see is snooze bar, right? Hitting the snooze bar. So we'll say we got snooze is one event, and making it to class on time is the other event. So we're going to have like A, B, snooze, which when we label things later, and we'll have event B, B on time. This will just allow us to use some notation later. For our tree diagram, we're going to have, we'll just start with the alarm as our start. From the alarm, we have two choices. Right? Mr. Mosley, I'm either going to hit snooze or I'm going to wake up. Those are the two options. The probability I hit snooze is 0.6, meaning there's a 0.4 probability that I wake up. Right. From these two options, I have two other choices, or essentially two other outcomes. Right? I can be on time or late. Right? Probability that I'm on time. Let's see, we have 0.9 probability that I make it to class on time. That's when I hit the snooze bar. So if I hit the snooze bar, right, I have a 90% probability that I make it on time. If it doesn't, oh, sorry. If I don't hit the snooze bar, sorry, wake up on time, 0.9. If I hit the snooze bar, I only get a 70% chance or a 0.7 probability that I make it on time. Right, so that leaves 0.3 here and 0.1 for the other part. So this is the entirety of the tree diagram. It goes through the progression of the options of once my alarm goes off. All right, so it's a series of events, a sequence of events. Now the question I'm answering is, what is the probability that Mr. Mosley is late? All right, so let's look. The probability that I'm late, right? There are two routes through the tree that result in me being late. One with the snooze and one with the actually waking up. Right? So we can have snoozing right, and late. It's one route through. If we wake up on time, we can be late through this route. So, in this problem here, we have one route is the probability that I snooze and I'm late. And the other route is that I wake up and I'm late. Right? Based on the rule that we just learned, right? The probability that I snooze and am late, right, is equal to the probability that I'm late, given that I hit the snooze button, times the probability that I hit snooze, plus the probability that I am late, given that I woke up, times probability that I woke up. Right, and this is just using the new general multiplication rule. So when we look at that, essentially, I multiply the numbers as I work through the tree. 0.6 times 0.3. Right? 0.3 is the probability that I'm late given that I hit snooze. And then the probability that I hit snooze is 0.6. Same thing happens here. We do 0.4 times 0.1. Give me 0.18 plus 0.04, which is 0.22, or 22%. So the probability that Mr. Mosley is late for class, about 22%, or 0.22. What can I clarify in this example? Do we need any time to write any of this down? Continue with the same example with a different question. Suppose Mr. Mosley is late for school. What is the probability that he hit the snooze bar that morning? Right, so in this problem, we are trying to find the probability that I'm late given I hit snooze. Oh wait, sorry, that's backwards. That's not the given information. See, where we can get into problems. Sorry, the given is that I'm late for school. So we need the probability of snooze given I was late. Now we go back to the previous lesson where we talked about the conditional probability rule, and that says this needs to be equal to the probability of hitting snooze and being late divided by the probability being late. Well, I just found both these numbers on the previous slide. Probability of being late is 0.22. Right? That's what we found here. Right? Probability of being late ends up being 0.22. We also already found the probability of hitting snooze and being late. Okay. That's this one right here, which is this, and ultimately this. So we have both the numbers we need already. So we come back over here. And we fill in our fractions. And we get the probability of snooze and being late is 0.18. But the probability of being late, 0.22. Okay. And one button. We get 0.8181818181 repeating forever. Right? Approximately 0.818 or 81.8%. Or we can say approximately 82%. This is the probabilities that I hit the snooze button, given that we know I was late, about 82%. Okay. Are there any questions? Does anyone need a moment to write anything down? All right. So now we have one more example we're going to look at. If you have been not paying much attention so far, and now is the time you're hearing my voice, please pay attention to this next example because it is very, very, very similar to the discussion board problem. All right? This is a good one to follow along with or take notes with. So, the next problem, we don't have enough room to do on this page. So it's going to jump over to OneNote, and this will be available in the class notes. We're going to switch over to here. All right. So here's our example. We have the Kaiser Family Foundation recently released a study about the influence of media in the lives of young people aged 8 to 18. In the study, 17% of the youth were classified as light media users, 62% were classified as moderate media users, 21% were considered heavy media users. Of the light users who responded, 74% described their grades as good, while only 68% of the moderate users and 52% of the heavy users described their grades as good. All right. Situation is we're going to select one of these young people at random. First, we're going to draw a tree diagram so that we can model this situation along with its probabilities. So we have a young person we're going to choose at random. And there are 3 options from this person. They are either going to be a light media user, a moderate media user, or a heavy media user. So we'll go with light, moderate, and heavy. And the probabilities go along with that. We have 17% or 0.17, 62% or 0.62, and 21% or 0.21. From this set of branches, oops, that's not what I wanted to press, we get 2 options. Right? The user either is going to identify as having good grades or bad grades. Good or bad. Right? And the light media users, 74% describe their grades as good, so we have 0.74, leaving 0.26 for bad. Right? Wherever from a source, the branches coming from a source have to add up to 1. Right? It has to account for 100% of the probability. Right? For the moderate users, 68% reported good, leaving 0.32 bad. And for heavy, we get 0.52 on good, leaving 0.48 for bad. So this is our tree diagram. Do we have any questions on how the tree diagram was created? Okay. So now question B says, find the probability that this person describes his or her grades as good. We want the probability grades are good. In this case, because there are 3 branches, there's 3 ways to get to good grades. Right? If we're going from light media users, right, that's one way. Moderate, another way, and heavy, the third way. So we're going to be adding up these 3 chunks to get to our probability. All right. So let's have, we're going to have A, B. Yeah, it's not going to help. Never mind. Because the amount of different options is not going to work out. So we'll just say we need the probability of being a light user and good, plus probability of moderate and good, plus probability of heavy and good. And again, based on our previous examples, the easy way to do this is to just multiply the successive probabilities, right? The sequential probabilities. So we have probability of light and good is 0.17 times 0.74 plus probability of moderate and good is 0.62 times 0.68 plus heavy and good is 0.21 times 0.52. Right? So we get these numbers here. And when we multiply and add everything together, we get 0.6566, or 65.66%, or we can say that's approximately 66%. And I'm showing you the different ways to represent the answer. Sometimes your answer may be requested to the nearest whole percentage. We round. Otherwise, we want to keep as much accuracy as possible and keep our decimal places, or just keep it as the original decimal representation. Those are all good options. Any questions on this part of the problem, part B, and how we got there? Good. Okay. So now let's look at part C. All right, so part C, we have given that this person describes his or her grades as good. We have given, good. This is our given thing. So now we're looking at a conditional probability. What is the probability that he or she is a heavy user in media? So for this problem, we're finding out what's the probability of heavy given good. Again, I want to stress, you need to correctly identify what probability you're finding, what's a given, what's not given, before you can actually solve the problem. You can't just like throw yourself into it. So in this case, we have the probability of heavy given good, which, again, based on our previous work, we know that we use the conditional probability rule, which is the probability of heavy and good divided by probability of good, which we have these numbers already. We have the probability of good right here, and heavy and good is this one. So we have 0.21 times 0.52 divided by 0.6566. And once again, we get out our handy dandy calculator. And we get 0.166 approximately. 0.1663113, and I'm sure there's more. All right. Or you can say 16.6%. And that's it. So this is how we use tree diagrams and conditional probabilities and the general multiplication rule. Right? What can I clarify? All right. So then jump back over here and look at the discussion board real quick for today. This is using the general multiplication rule and tree diagrams. So in this example, or this problem, we have a computer company makes desktop and laptop computers at factories in 3 states, California, Texas, and New York. California factory produces 40% of the company's computers, Texas makes 25%, and 35% are manufactured in New York. Of the computers made in California, 75% are laptops, meaning 25% are desktops. Of those made in Texas and New York, 70% and 50% respectively are laptops. So the 70% goes with Texas, the 50% goes with New York. And again, we can use the leftover amount to see what percentage is desktops. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center. Construct a tree diagram to represent the situation. Find the probability that the computer is a laptop. And then, given that a laptop is selected, what is the probability that it was made in California? Right? So it's essentially all the same things that we did for the example you guys just saw. Essentially just different numbers. Okay? It's going to follow along basically the same process.